So are there any questions? Did anybody try the homework? Yeah.
Okay, how do you assemble the global matrix?
How do we assemble the global matrix? So take a look at the solution for the truss code that I posted. So for the two-dimensional truss, again, you will have 2 degrees of freedom at each node, right? So the almost the exact same lines of code that I had there. See how the element degrees of freedom are being constructed for the truss problem. So using the same thing, you can construct your element degrees of freedom vector in MATLAB for the three-noded triangle. Okay. Any other questions? So one thing, so one thing I should mention here is that in your element routine, um, we in all our formulation we assumed that the node numbers have to be numbered counterclockwise, right? X1, X2, X3. So if you don't number them counterclockwise, then the area that you compute using determinant, so something like um, right. So for this, for example, if you have the node numbers 1, 2, 3 in the counterclockwise, then the area that you compute using this, all this formula, using this determinant, that will come out to be positive. But if it is in the clockwise direction, then it will the area will come out to be negative. So that can affect not only the area but also some of these coefficients. So make sure that if the node numbers are given to you in a clockwise manner, calculate the area and see if it is coming out to be negative or not. If it is coming out to be negative, then you know that the node numbers are actually in a clockwise direction. So you might have to change some of these A1, all these A, B, and C coefficients also. Basically, the idea is that we want to construct shape functions that go to 1, not -1, right? So, so you have to keep that in mind. Um, all right, so what we were doing last time, we started to take a look at this general Q4 element. And we said that we have this, we know how to construct our shape functions for a square, which goes from -1 to +1. And what we will do is use this thing called an isoparametric map. So what we'll do is we will pretty much take whatever function we have on our parent domain. So this is called the parent domain. Whatever function we have of c and eta, we are going to map that to its same value at the location at the real x and y, which is actually a element in the real mesh. So this kind of a mapping is called the isoparametric map, where we use the exact same shape functions that we use to approximate the displacements. We use the same shape functions to map all our functions from the parent domain to the actual domain. Um, and we can express this relationship if we use the isoparametric map. This relationship is very similar to what we had for the finite element approximation, right? We used to say that the displacement will be equal to shape function matrix times degrees of freedom for the finite element. Here we are doing the very similar thing, that the xy coordinate corresponding to some c and theta are going to be shape functions times the actual coordinates. So this is nothing but a map that allows you to go from c eta domain to xy domain. Okay. And we also saw that some of the we can express all the 4 shape functions for alpha is equal to 1, 2, 3, 4. So if you plug in alpha 1, you will get shape function 1 and so on. This is a general formula for all the shape functions, and we also saw what that looks like in terms of how the mapping works. So okay, now that we know how to calculate our shape functions on the actual domain, we know that all that we have to do is to map our shape functions from the parent domain that we already know. We just have to map those shape functions to the new domain. So now we have the shape functions on our actual domain. But how do we start to calculate gradients? That's a little bit more tricky. So obviously, the gradients in this actual domain, the rate of change of any function in the x and y in the actual domain is not going to be the same as the rate of change versus c and eta. So to calculate all those gradients, we started to say that we'll take a chain rule, and what we essentially want is, let's say, the derivative of shape function, each of the shape functions with respect to 1 and 2. That is, derivative of the shape function with respect to x and with respect to y. These derivatives are not with respect to c and eta. So this is something that you absolutely have to understand, that when we are solving any finite element problem, we want to calculate things on the real domain, and then we will map them back to the parent domain to do our integrals. So all these derivatives have to be with respect to the real xy coordinates. And we saw that to calculate all these derivatives with respect to x and with respect to y, we're going to use the chain rule. And the way we set up the chain rule was in a reverse sort of a manner, that we know how to calculate this. This is, if you just write the chain rule out, this is the two-term chain rule for n alpha with respect to c, similarly n alpha with respect to eta, and you can express that in this matrix form. So as we saw last time, this matrix is Jacobian transpose. Okay, and on the next page, we actually saw how to calculate that Jacobian matrix. So so we said that since we need to calculate all these dx, 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 d eta, dy, dx, and dy, d eta, you can actually just take this entire 4 terms, and that would be your Jacobian matrix. That's the definition. And in order to calculate each one of these 4 terms, all that we are going to do is take our isoparametric map, take the derivatives of this entire equation with respect to c. That is going to give you all these derivatives with respect to c. So n1, n2, n3, n4, those will be the derivatives with respect to c, and the coordinates will remain as same because they are constants. So in this way, this is a really sort of a roundabout, long way of calculating the Jacobian, but there's pretty much no other way to do that. So why we are doing this, why we are calculating the Jacobian, because we want the derivatives in the actual domain. Okay, since we want the derivatives in the actual domain, we have to calculate this Jacobian. And once you calculate your Jacobian, you can take its inverse and then take its transpose, or you can transpose and then inverse, it doesn't matter. Once you have this matrix, now you can go back and try to find out your n alpha, and now you can plug your n alpha and with respect to x and with respect to y in your expression for the B matrices. So now you have this, you already know this. This is on the parent domain, and this is something that we just calculated using this sort of long procedure. Okay. So finally, all the steps are pretty much written right here. You have once you are given the coordinates, the 4 coordinates of a quadrilateral element, the first thing you actually do is to calculate the shape function derivatives on the parent domain. Once you calculate the shape functions from the parent domain, you can calculate j. J is right here. And in j, all these 4 terms, all that they require is these 4 quantities, because you already know x alpha and y alpha. So in this case, now you have j. Once you have j, you can calculate j inverse transpose, and then multiply those derivatives with that, and you will have the actual derivatives. So once you have these actual derivatives, you can go and plug them into your B matrix. So that B matrix was your was the derivatives of all the of the element quantities that we had calculated before. So so these were the B matrices for the heat conduction problem, and after that we are still not talking about how we are going to do the integral, but we know how to calculate the B, the K is given, this B, and so on, N transpose and all those terms we know how to calculate now for the actual element, not the parent element. And the same thing for elasticity matrix, and after that you already know how to assemble that, assemble the two matrices and solve this equation to get with by enforcing boundary conditions, and that will give you the solution. So what we're going to do today is try to find out how do we do this integral, because all that we have done till now is that we have an actual element in the real domain, xy domain. We have been able to form these B matrices and these N matrices, which are shape functions and shape function derivatives on the actual domain. Now, what we need to do is to take this entire integrand and do an integral over that element. So how do we do that? What we are going to do is use numerical integration. Okay. So the idea is that to do any kind of numerical integration, I'm denoting that integrand with some quantity, this dot. Okay, and this dot is basically some sort of a function that you need to integrate over the area. And similarly, you have the boundary terms that you would have to integrate. That's just some term over the length of the boundary. So those are the two types of integrals that are involved in our problem. So if you just take a look at the previous page, this is the boundary integral, and these two are the domain integrals. So those are the two integrals that we are trying to find out how to evaluate. So in 2 dimensions, we'll take a look how we do that, but let's take a look at how we do that in 1-dimensional case. How many of you are actually familiar with Gauss integration in 1 dimension? Trapezoidal rule, I'm sure you heard, and Simpsons rule, maybe you heard. So that this Gauss integration is just a little more generalization of your of these kinds of integration formulas. So anyway, so the idea is that we have this function. We have some function of x, and we want to integrate that function from between the limits a to b. And we know that that integral, what that represents is this area under the curve. So this integral is nothing but this area under the curve. And if you think about, like, this is our actual element in the mesh, and this is our parent domain. This parent domain goes from -1 to +1. And the actual element could be anything, could go from A to B. So what we are going to do is we are going to use this isoparametric map, which uses the shape functions from 1 dimension. This is the 1-dimensional shape function. And you can see that if I plug in the value of c as -1, I get into this expression, then I get -2 divided by -2, that is 1, that is a right here. So -1 is mapped to a, +1 is mapped to b. Everything in between is a linear map. And it's linear only because we are choosing these shape functions. If we were to choose the 3-noded shape function, it would not be linear. Okay, especially if you use the 3-noded element and the middle node is actually not at the half location. If it is a little bit offset, then what you would be doing is mapping this length to somewhere to a shorter element and this length to a bigger element. So you have to keep this in mind later on when we talk about higher order elements. This mapping need not be linear. But if you are using linear shape functions, then this mapping is going to be linear. Does that make sense? Okay. So essentially what this map is nothing but a change of variables. And this is something that I'm sure all of you are familiar with. And So the change of variables, what we are saying is that we will express this integral now in terms of c, and uh, our formula for x and c is right here. So using this formula, I can calculate dx over dx, which is nothing but this first derivative times a, second derivative n2 derivative with respect to c times b, and that turns out to be this. And if you rearrange that, this is what it is. So can anybody take a guess at what this is? I mean physically, 2 over b minus a. So b minus a is what? That's the length of this thing. What is the length of this? 2. So this is nothing but the ratio of the two lengths. Okay, and we also denote this thing with Jacobian in one dimension. This is nothing but the Jacobian in one dimension. So we just talked about the Jacobian in two dimensions. This is nothing but Jacobian in one dimension. Um, so the idea is that now that you know that dx is equal to j times dc, all that you need to do is you substitute for all those things in your original integral. This was the original integral. I substitute dx with j times dc. That's right here. And now I will have a new function of c. So I have modified my original integral, transformed it to a variable c. And the reason that I'm denoting it with a different function f hat is because it is actually a different function. So for example, here, if you take a look at the side note, let's just consider, for example, one small function f is equal to x squared over the domain -2 to +2. Okay, so if you take this f is equal to x squared, and if you map it to f to a function, basically if you take that function and compress it to go from -1 to +1, the actual functional form over c is going to be different. So in this case, you will see that x is equal to 2c, where obviously if c is -1, then it maps to -2. If c is +1, then it maps to +2. It should be here. Um, and so the function of x is x squared, and the function of c is 4 times c squared. And the same type of idea will generalize to 2 dimensions and 3 dimensions. So essentially what we are trying to do is we are trying to integrate all this f some function of c times the Jacobian. And here you need to also keep in mind that this Jacobian in this case is just a ratio of lengths, but in general it will not be constant. This Jacobian will depend upon c, because just like I told you right now, if it's a 3-noded element, this part of the Jacobian will be different, and this part of the Jacobian will be different. So this Jacobian will also depend upon c. So all this integrand will be a new function of c, which you can denote as g. So so now what we want to do is, now that we have mapped our actual element back to the parent element, we want to calculate this integral using numerical methods. And to do that, what we use are generally called quadrature methods. So quadrature is nothing but another term for numerical integration. And one of the most common rules that we apply is the trapezoidal rule, which you are all familiar with. So just to go over it a little quickly, what we have is our domain from -1 to +1. We are going to divide it into n parts, and these n parts need not be equal. Okay, but let's say, if just to keep things simple, if they are equal, then each of those small lengths delta L is going to be equal to the total length, which is 2, divided by the number of parts, which is n. So that's your small delta L right here. And the way trapezoidal rule works is you go to the middle point of each of those trapezoids and try to calculate the area of this trapezoid by using the value of the function at this middle point multiplied by delta L, and you sum all of them up. So that's your trapezoidal rule. And another way to express that is like this. So you take the value of the function g. So you also keep in mind that originally we were trying to calculate this integral of f over a and b. Now we have modified that integral to a new function g over c. So to calculate this trapezoidal rule, you instead of going and calculating your function values at the middle point, what you can also do is calculate the function values at the boundaries of all those trapezoids. So if you calculate your function values at the boundaries of all those points, then you don't have to calculate. Then actually that helps you in implementing it in a little faster way. So the idea is that half the length, half the delta L goes to this way, half the delta L goes this way. So all these values get summed up by twice, and the end values -1 and +1, they get only half and half. That's your trapezoidal rule. Does that make sense? Okay. So a similar rule is called the Simpsons Rule. And in this Simpsons Rule, the idea is that you will take your integral -1 to +1 again, and you will divide it up into n parts. Again, they need not be equal, but just to keep things simple, let's assume that these n parts are equal. But there is a further restriction that the number of parts have to be even. You cannot divide it into odd number of, so n cannot be 1, 3, 5 or something like that. N has to be 2, 4, 6, 8 and so on. And the reason is that the way Simpsons rule works is by approximating your function using 3 points. So in 3 points you can fit a quadratic exactly between 3 points. So earlier it was a trapezoidal rule, you were fitting a linear function through that. Now you are fitting a quadratic through 3 consecutive points. So if you consider only the bottom curve, this green curve, this is one function from here to here, another quadratic function from here to here, and another quadratic function from here to here. So if you use this kind of a rule, then it turns out that for this is called the composite Simpsons rule, because you have divided your interval up into many different parts. So you can express your formula. Your formula for the integral can be approximately expressed as delta L over 3, where again delta L is this, times the value at the two nodes, -1 and +1, this one and this one. And there are certain nodes which actually belong to the middle point of the quadratic approximation. So you can see that this is the quadratic approximation between these 3 nodes. The middle point of here, all these points get a weight of 2, or get a weight of 4. All the points that join 2 quadratic curves get a weight of 2. So that's the 4 weight here and the 2 weight here, and this is what you get for your Simpsons rule. Okay. And if you want the exact formula for computer implementation, the exact location of all these points you can find with these relationships. So this is nothing but trying to fit different types of curves through our regularly spaced points. And so here is a little bit of a statement that all these methods, these trapezoidal rule and these Simpsons rule, these rules belong to a special class of quadrature formulas. Does anybody know what this class of quadrature formula is called? So this class is called a Newton-Cotes quadrature. Or Newton-Cotes formulas. And the entire supposition of this quadrature formulas is that given some points, you are going to fit and a degree of polynomial through those points, and whatever integral you get from those polynomials, because polynomials you can integrate exactly. So all these functions you can calculate from, all these weights you can calculate from those integrals of the polynomials. So in general, all these formulas, if you take a look at all these formulas, what they look like is the value of the function at some point, all these values of the function at some point times some factor, right? So in this case, the factor is 1 times L over 3, this is 4 times L over 3, this is 2 times L over 3, and so on. So all those factors are right here. These are called weights, okay? So all you are doing is you're calculating the value of the function at some point, multiplying it with some weight, and you're saying that my integral is going to be approximated like that. So using this logic, Gauss came up with another integration scheme where he said that, well, let me not choose all these points a priori. Let me not choose these points beforehand and then try to fit a polynomial through it. What we'll do is let's have two types of two independent parameters. The location Ci. So in this case, all these locations were fixed. But if we choose the locations also to be variable and the weights also to be variable, then for each quadrature formula, we will have 2n parameters. Okay. So if we choose n number of points, we will have 2n number of free parameters, the location of this C and the weight that is going with it. So if you have 2n parameters, you can fit a polynomial of 2n minus 1 degree exactly. Okay. And that's the entire premise of Gauss quadrature, but the derivation is a little more involved and it's not even that important for us right now. So what I'm giving you here is this table of locations Ci or Cj times weight j. So in this case, you can see that this is a table that is coming directly from Zienkiewicz and Taylor. There are some more details about Gaussian quadrature there if you want to take a look at that. But this function f is our function g of C. Okay. So the idea is that if you go to location 0, which is right here, and you take the weight, which is 2, then what we are saying is calculate the value of this function at 0, multiply that with 2, and this area under the curve, which is a rectangle, that is going to be approximately the area under this curve. And to what degree is this area going to be exact? So I'm saying that, or if I use this first rule, one Gauss point, the Gauss point location is 0, the weight is 2. I calculate the area of this rectangle, which is whatever the function value is here, times 2. And that value is going to be accurate up to a certain polynomial degree. And that polynomial degree is going to be linear, because if you draw a line, let's say your function is something like this. So what happens is that this area and this area cancel each other off, and whatever you get from this approximation is going to be exact for linear polynomials. Okay. So the similar thing happens in this case, but now this is a 2-point Gauss quadrature, and the 2 points are plus minus square root over 3. So minus 1 upon square root over 3 plus 1 upon square root over 3. And you go and calculate the function value at that point, multiply it with its weight, that's 1 right here. Similarly for this one, that's right here. And now, how many, to what degree of polynomial is this going to be accurate up to? Actually more, because there are 4 parameters in Gauss quadrature. If you use a 2-point quadrature, you have 4 parameters, the location and the weight. So when you have 4 parameters, you can fit a cubic exactly, which means that if you use this formula, calculate the function value at this point, calculate the function value at this point, multiply by their weights. You can exactly integrate a cubic, and this sort of looks like a cubic. So you can see that this rectangle and this rectangle put together is going to be equal to the area under this curve. Not approximately, equal to. It is going to be exactly equal to the area under this curve if this curve is cubic. So the similar thing happens for higher orders. In this case, you have 3 Gauss points. So what would be the order of the polynomial that you can approximate exactly, integrate exactly? 3 times 2 is 6 minus 1. So 5th order polynomial you will be able to exactly integrate using this Gauss quadrature. So similarly, you have many more numbers actually in the table. You can go up to whatever order you want. But typically we do not use points more than 3 or maximum 4 when we want to use when we want to use these numerical quadratures. Okay. So all right. So now that we know how to do integration in 1 dimension, let's try to see how we can apply this Gauss quadrature to our original problem. The original problem we had was integral over the domain, that is the integral over the actual domain. And this is a 2-dimensional integral. Okay. So so let's take a look at first these domain integrals. So what I'm denoting here is that we need to integrate some function over this domain. And I'm denoting that domain with this solid square. Okay. And the boundary integrals are denoted with this empty square. So what we want to do is we want to calculate this quantity, and to do that what we need to do is to map this small element of area from this actual domain back to the parent domain. And this mapping is actually going is also the isoparametric map, but in general this mapping is in curvilinear coordinates. So how many of you have heard of or used curvilinear coordinates before? I'm sure you have actually, but you probably don't remember. But anyway, so this is part of the derivation. So as long as you follow the derivation, it will not be that hard to code it up actually. So the idea is that this small element of area, when your element is arbitrarily oriented in x and y, you cannot say that this small element of area is dx dy, right? So what we want to do is we want to construct a local coordinate system at this point, which we call the curvilinear coordinates. So just try to imagine that you have some kind of a sphere, let's say. We have heard of Cartesian coordinates, that's x, y, z. We've heard of cylindrical coordinates, that's r, theta, and z. Spherical coordinates is r, theta, and phi. These curvilinear coordinates are actually trying to trace a curve in space. Okay, and at each point you still have your regular. Actually, in this case, you may not have the this angle between these 2 points. These 2 vectors need not be equal to 90 degrees. So the curvilinear coordinates, they just try to trace out some path in a 3-dimensional space or 2-dimensional space. So in this case, we are saying that we'll make this small curvilinear coordinates x hat and y hat, and the area, this element of area, now we can express this element of area as dx hat times dy hat. But keep in mind that this dx hat and dy hat is related to your dx and dy. And that relationship is again something that you might have learned long back in vector calculus. But what you will see is that the similar sort of transformation, change of variables, what we did in 1 dimension was change of variables. We are doing a similar change of variables from x hat, y hat to c and eta. Okay, so going from x hat, y hat to c and eta, that's the change of variables that we are doing. And if you use that change of variables, you have to express dx hat, dy hat in terms of dc and d eta. So this is the element of area in the actual coordinates. and this is the element of area in the parent coordinates. So you will see that if you want to convert this dx, dy to dxc and d eta, what you need to multiply it with is with this. And if you you can actually show using chain rule and all that, that this quantity is nothing but the Jacobian that we were just talking about. Now this Jacobian does not involve x hat and y hat. This Jacobian involves the real x and y. So we can calculate, and we know how to calculate this Jacobian. It's a little bit long, roundabout way, but we know how to calculate this Jacobian. All that this involves is calculating all these four terms. So we will calculate all these four terms again using the shape functions. Just go back and take a look at your notes from for that Jacobian thing, how to calculate all these four things. And now we have mapped our integral from the actual domain, the solid blue square, to +1 to -1 over c and eta. And this integral we know how to calculate. Okay. So in order to calculate this integral, let's consider this first one. We know now this is a one-dimensional integral, the one inside, and we can calculate that using the same Gauss quadrature. So we are approximating all this with g. You calculate that value of function at some different sets of I, and then you calculate the outer integral. You will have this double summation. So all we are doing here is, so for example, let's say you have this real element in a real mesh. Now you want to calculate what is the value of the integral of some function over this real element. So what you do, go back and calculate your j from the given shape functions, and then calculate the value of this function. They calculate the value of this function at all these 4 points. So these 4 points are coming from 2 cross 2 Gauss quadrature. What we are saying is we'll use a 2-point Gauss quadrature in C. So that's right here and right here, plus and minus 1 upon square root 3, and 2-point Gauss quadrature in the eta direction, that is plus and minus 1 upon square root 3. So that gives us 4 points. What that means is you calculate the value of this function at all these 4 points, multiply it with the weights, and you will have an approximate value of your integral. So this is just a generalization of your one-dimensional integral. So if I use a 2 cross 2 Gauss point, what will be the value of Wi and Wj? One each. So Wi will be 1, Wj will be 1, so multiplication of those two will be 1. If I use a 1-point Gauss quadrature, that means that I'm just choosing 1 point right in the center. What would be this? 2 and 2, which means 4. And that makes sense because what I'm essentially saying is calculate the value of the function at this point. So try to imagine you have a square plate and you have some 3-dimensional function over that. What we're saying is calculate the value of the function right in the middle of the plate and multiply it with the area of that square. Area of the square is 2 times 2, 4. That's 2 times 2, 4 right here. So the same sort of physical interpretation that we had in one dimension, what we are doing is we are calculating the value of this point, multiplying it with this area, calculating the value of the function at this point, multiplying it with this area, and so on. And for higher order quadratures, if it is 3 cross 3, similar things happen. Okay? So this is how we basically calculate all the integrals that we had over the domain. So we now know how to calculate this entire term. That is, we know how to calculate k element and the body force part of our force. What remains now is to calculate these boundary integrals. So let's take a look at that. So for the boundary integrals, it's not that complicated in 2 dimensions, but in 3 dimensions, it is a little more complicated. So we'll just try to use some general, talk about it a little more generally here. So what we are trying to do here is calculate the integral of something over the boundary of the element. So this was our element, and we have this function that we need to integrate along the edge. That was coming from if you have some domain, and if you apply a traction on the boundary, then you would have to integrate that traction on the boundary. So in this case, again, what we are going to do is we are going to map our edges. So this is edge 1 to 2 that gets mapped to edge 1 to 2 on the real element. And if you take a look at small length of this in the actual element, this is the length dl. You can express this as dx plus dy. Dx, this is as a Pythagorean theorem in this form. Okay. And if you use that, you can also see that to calculate dx and dy in terms of dc and d eta, what again you would do is use chain rule. So whenever you have all these kinds of mapping from one domain to the other, your best friend is the chain rule. You have to apply chain rule to calculate all these different quantities. So if you apply chain rule here, let's see what happens. This dl is in terms of dx and dy. Now we want to express this dl in terms of dc, because along this edge eta doesn't change. Eta is equal to -1. Only change is in c. So if you apply the chain rule to this expression with respect to c, you would get dx by dc times dc. And if you square it, you can pull that dc out, and what you would get is this thing for edge 1 to 2, and the same thing for edge 2 to 3. The only difference is that on edge 1 to 2, the value of eta is constant at -1. From edge 3 to 4, the value of eta is constant at 1. So this is coming nothing but from the chain rule. And there are no derivatives in this with respect to eta, because eta is constant. Okay, so this is a little bit of a vector calculus. If you take a look at it, it's not that hard to follow. You had a question, Ali? These or this? So these are the x hat and the y hat coordinates. These are the curvilinear coordinates. These will in general not be perpendicular. But this is a global coordinate system that we have chosen to define our property, so we can choose these to be perpendicular. So finally, for the edge 2 and 3, same thing happens. This is edge 2 that goes from 2 to 3, and in this case, c is constant, but eta varies from +1 to +1. So once again, using your one-dimensional formulas, you can express these integrals. So whatever integral you have in terms of dl, you can transform that integral by using this relationship. Now you know what dl is. It is this quantity times dc, or this quantity times d eta. Plug that in here and use your one-dimensional formulas, and you will have the integrals over your edge. So this is also sort of related to the three-dimensional case, and I think I should have also mentioned this on the previous page in the domain integrals. In one dimension, we just told you that the Jacobian, is a ratio of the final length to the initial length. That's the one-dimensional determinant of Jacobian. So there is no tilde under the j. It's a scalar. In 2 dimensions, the Jacobian is a 2 cross 2 matrix. And if you take the determinant of that 2 cross 2 matrix, that is the ratio of this area to the small elemental area in the parent domain. In 3 dimensions, this is something that you should remember from mechanics, that the change in volume is nothing but determinant of j, where j is pretty much the same as your deformation gradient. And this is also something that we talked about in the first few lectures. So if it is one dimension, your j or the determinant of j is relating your size of the domain. The same thing happens in 2 dimensions. In 2 dimensions, in 3 dimensions, we know how to calculate the rate of change of area. So does anybody remember this Piola area transformation rule? If you have a body, a 3-dimensional body, and if you deform it, the surface area of that body will change, and that relationship is given by this Piola transformation. And an easy way to look at that is like this. So let's say you have some 3-dimensional body, and on the surface you have this dn1 and dn2. Okay, so so I guess let's say this is n1, n2, and this is the vertical, the normal pointing to that on the surface. So there's a 3-dimensional body. I'm placing this point on the surface somewhere. This vector is the actual direction of the area vector. Area is actually a vector. So that area vector is calculated by n1 cross n2. If you take n1 cross n2, you will get the outward normal. That is the area vector for in 3 dimensions. If you deform that body, that area vector is going to get mapped to a new place, but you just cannot say that we will deform this with f. What happens is that these two vectors get deformed with f, or in this case it would be j. So dn1 gets deformed to this vector, and that vector can be calculated from this relationship. So dn2 is j times dn2, and if you pre-multiply this entire equation by j transpose, what you get is j transpose times dA, and the right hand side can be written in terms of determinant of j. So this is a 2-step derivation of how to use this Piola transformation, or this Nansen's formula that relates the area change as things deform. Okay, so now that you have all these integrals, you know how to calculate the boundary integral, you know how to calculate the domain integral. After that, it's a very simple step. For heat conduction, you know how to calculate all these integrals. This is you take this integrand right here, calculate it at the value Ci and Cj, that is the 2 cross 2 Gauss points, let's say, multiply those to the weights, multiply that with the Jacobian at that location, and sum all of them up. You will have an approximation for your element stiffness matrix. The same thing for the force vector. You will have this over the boundary, this over the domain and this over the boundary. And the only difference between this heat conduction and elasticity problem is that D matrix here and this kappa matrix here, that's the conductivity, and this is the elasticity matrix. The dimensions are also different because this is going to be 8 cross 8 and this is going to be 4 cross 4, because this B matrix is 2 cross 4 in this case. So finally, you can assemble all of those element stiffness matrices, solve your boundary condition, and then do some post computation. So we'll take a look at this post computation for Q4s next time, and take a look at your homework also. If you have any questions or if you have any doubts about the code, MATLAB or anything, post it to the forum. And it's important to do this because we all need to, you all need to sort of collaborate and learn together. You can struggle with your code for hours and hours and not learn that much. But if somebody's already taken a look and found a problem, that's why we are trying to use this forum that much. Okay? All right, so see you guys on Friday.